Okay, good evening everyone, and welcome to the Royal Academy of Engineering. My name's Jane Wernick, and I'm a structural engineer and a fellow of the Academy. As you know, this lecture forms part of the Royal Academy of Engineering's London Design Festival events of 2010, and our theme this year is designing a low-carbon infrastructure for London. Before I go any further, can I ask you to turn off your mobile phones? And also encourage you to go and see the great exhibition downstairs about the Druck White Lotus School in Ladakh, which has been designed using sustainable principles, local labour and materials, etc. So our speaker this evening is Doug King, who is a consulting engineer who specialises in the application of building physics to the design of low environmental impact buildings. He graduated as a physicist and then turned his attention to buildings. As a fellow of CIBSE and the Energy Institute, he is therefore a chartered physicist, an environmentalist and an engineer, a good combination. He has contributed to a number of groundbreaking buildings in terms of sustainable design. These include the Sainsbury's Eco Store at Greenwich, the new Rolls-Royce factory at Goodwood, the Genzyme Centre in Boston, which is the largest LED platinum building in the world, and the innovative green office which still, he believes, has the highest BREEAM scored building ever. Doug is the founder of the award-winning engineering practice, King Shaw Associates, and he has taught for many years. Currently, he is the Royal Academy of Engineering's visiting professor of building physics at the University of Bath. He authored the recent Royal Academy of Engineering report, Engineering a Low-Carbon Built Environment, but he's probably better known for continuously saying eco-bling to journalists. Doug, I'm delighted to invite you to give your lecture now, Engineering UK Buildings for Zero Carbon.
I'm not going to dwell on climate change. If there's anybody in the room that doesn't believe it's happening, they really ought to take a look at the science. As far as I'm concerned, it's probably too late to be talking about mitigation, because if we look at the historic record for atmospheric carbon dioxide as captured in the polar ice caps, I'll give you a little bit of background here. Because in the Arctic it snows once a year, the snow consolidates and becomes a layer of ice in a glacier. You then get a slight thaw on the surface, which gives you a skim of ice, and then it snows again the next year. So if you were to take a core drill out of the ice cap or out of a glacier, you can count the layers of ice in exactly the same way as you can count the growth rings in a tree trunk, and you've got a timestamp. You can go back through history. If you extract water from that ice at a particular depth, you can measure the carbonic acid in the water, which gives you a measure of the carbon dioxide in the atmosphere at the time that the snow fell. So we have a historic record of carbon dioxide in the atmosphere. We also have readings this part of the graph from direct measurement of atmospheric carbon dioxide from meteorological balloons. And I'll leave you to speculate on the reason why carbon dioxide concentration in the atmosphere has run away exponentially since about the beginning of the 20th century. That curve, the famous hockey stick curves, looks an awful lot like the temperature anomaly curve, which the Hadley Centre produced a number of years ago to indicate the scale of likely future climate change. So it's happening. We're not talking about stopping climate change. We're now talking about dealing with the effects of climate change and reducing the scale of further climate change. How has this all come about? Well, I suggest that throughout the history of mankind, up until the Industrial Revolution really, we had a direct relationship with our energy sources. Energy was something we had to work for. In fact, it was our own energy, and therefore we valued it. We discovered the black gold, and that changed everything. Now, suddenly, we've got a hugely concentrated energy source which we could exploit in all sorts of ways. That allowed us to industrialize our energy supply. And by industrializing our energy supply and squirting it down wires to our buildings, we could suddenly do things that we'd never dreamed of before. We could build our cities. We could start to focus on aspects of life and society other than survival. note any similarities between those two slides? I think it's ironic that we're building sorry, forget it. Back in the 1950s, sorry, this is very difficult to read. The sources are down here at the bottom. Back in the 1950s, a Texas oil geologist, Marion King Hubbert, started studying the exploitation of finite fossil fuel resources and putting them in the context of some very well understood and irrefutable statistics. Something known as the logistics curve, which governs the rate at which you can extract and exploit any finite natural resource. King Hubbert used this mathematics combined with the rate of discovery and of abstraction of oil to date, plus the proven future reserves from test wells and from geological exploration. And he fitted this mathematical function to that data. And he predicted that around about the turn of the millennium, the global rate of production of oil would cease to rise year on year, and it would stagnate, and then eventually it would turn around and it would start to decline year on year. Now, if you think about it, that's kind of inevitable. If you're drilling holes at random all over the planet looking for oil, it's not quite that simple. They do put some intelligence into geological exploration. But if you were to drill holes at random all over the surface of the planet, the first oil fields you discover would be the really big ones, because you've got a good chance of finding them with one drill. Once you've discovered and started exploitation of all the really big oil fields, you have to drill more holes to get a strike next time, because the remaining fields are smaller. And they get smaller and smaller, and it becomes harder and harder to discover new oil. This holds true for any natural resource. And then the rate of exploitation, the rate of discovery, and the rate of pumping follows that rate of discovery, but with another twist. When you first drill an oil well, the oil in the ground is under immense pressure. It squirts out. We've all seen the pictures, haven't we, or the movies of gushers in America in the 1920s and the 1930s, when the oil simply poured out of the ground and contaminated vast areas before they managed to get a pipe on the top and do something useful with it. Well, after a few years, that pressure starts to drop as the oil's been pushed up. Eventually, the pressure in the well drops to the point where it no longer reaches the surface under its own volition. And then you have to start pumping. And all the time that the pressure's been dropping, the production rate has gone down. And then when you start pumping, the production rate goes down further. And then you start to pump away all the oil around the wellhead, and you have to wait for it to trickle in from all the remote parts of the reservoir. So your production rate goes down again. And eventually you have to drill an oil well all the way over there, but that one's for injecting water into the ground to try and push the oil to the point where you're pumping. So your production rate goes down again. And all of these things add up. And all of these things add up to a phenomenon known as peak oil. And King Hubbert predicted peak oil for the globe sometime around the turn of the millennium. In 1956, he predicted the peak of oil production in North America for 1969. He missed it by about 6 months. It actually happened in the early part of 1970. Okay. This is from David Strahan's website, the last oil shock author, if anybody's keeping up with that one. These are the coloured countries on the map, are all the countries that are producing oil or have oil reserves. All the ones in green are still on the up curve of production. All of the ones in red have already gone into permanent decline. What does that mean for us? Well, this is some work by Gilbert and Pearl that was published a couple of years ago, looking at different scenarios from different research groups and comparing what this might mean for us in the future. Now, these red scenarios up here are the International Energy Agency's scenarios for potential growth in demand globally for oil. And this is based on business as usual, and this is based on us in the Western world freely giving of all of our energy conservation technology to the developing nations so that they don't exploit fossil fuels in such an inefficient way as we did in the early part of our evolution, fuel evolution. And these various curves down here are various scenarios for future production based on different analyses of the oil well production data by different groups. What this says is, this graph doesn't start at zero, it starts way up here at 25 billion barrels a year. And what that says is, at the worst case, we could be looking at a global shortfall of oil production over demand of about 25% in just a decade. That has very significant consequences. This is the elephant in the room. All of our politicians are still talking about climate change and using climate change as the driver for energy efficiency. But nobody at a political level in the UK is talking sensibly about peak oil. There are other groups. There are groups of engineers. There are business leaders who are looking into the potential impact of peak oil in the UK. But our politicians are not dealing with this issue. And it's a big one. It's going to affect all of us. Have we got any evidence for these theories? Well, I don't know. This is a little bit of just tinkering with economics that I've been trying to do. Now, this is historic oil prices going back as long as I can get figures for the spot price for Brent crude, back to 1988. This is the monthly average of the daily closing prices, just to even out the sort of speculative market fluctuations. And I'm not an economist, so I'm not qualified to interpret this for you. But from what I have found out about economics is that this portion of the curve represents a fairly mature commodity market. The average price is stable, and the fluctuating price is driven by speculation, and it grows. The fluctuations grow over time as people buy more and more in and out. Now look at this. Around about 2002, something dramatic happens to the oil market. I don't know what that is, but something happened between 2000 and 2002 which has caused a complete change in direction of the market. Now, I can't interpret this for you. I don't know what it means. But I suspect that somewhere in this kind of data, there is evidence that nobody is owning up to. It's also interesting to note that when you do this kind of exercise, it shows up some pretty interesting things. Look at that. There is a peak there that corresponds directly to the collapse of the mortgage market in the States. There's a peak there that corresponds almost directly to the dot-com bubble bursting. And if you normalize oil prices against against GDP in the Western nations, right back to the 1930s, you can find a price spike in the oil price corresponding to every major recession or financial disaster since the Depression. And it's interesting, it's as we came out of the Depression that we developed the financial economy. It was in the 1920s and the 1930s in the States that you started to see people trading in stocks and bonds and shares and the development of that financial market. So I wonder, I'm prepared to stand up and say my thesis is that actually the wealth of nations for the last 70 years has been driven by the abundant availability of oil. And when that abundance looks to be threatened in any way, evidenced by these spikes in price, we see impacts throughout the global economy. So, what are we doing to address these issues? Our policy in the UK now, following the Climate Change Act in 2008, commits us to a 34% reduction in carbon dioxide emissions against 1990 baseline levels by 2020, that's 10 years away, and by 2050, an 80% reduction. We use 1990 as the baseline level because that was the baseline established under the Kyoto Protocol for measurements of greenhouse gas emissions globally. And of course, as a sub-strand of that policy, we have the policy that says that all new buildings must be zero carbon by 2020, with an earlier date of 2016 for schools and homes. How are we doing? Pretty good. Read the headlines. The government tells us we've managed to achieve a 12% reduction in greenhouse gas emissions against 1990 levels. Whoopee. we're winning, aren't we? I suggest not. Unfortunately, the recession kicks in again here and causes a significant reduction in carbon dioxide emissions as a result of the contraction in economic activity, which actually makes the rest of it look pretty pathetic. It looks even more pathetic when you look at the dates these things occurred. So we've achieved in carbon dioxide terms, rather than global, the greenhouse gas basket, just in carbon dioxide terms, we've achieved a 10% reduction since 1990. However, the Kyoto Protocol was only written in 1997. All our policies for climate change, carbon reduction, etc., have been introduced since the Kyoto Protocol in 1997. And in that time, we've only reduced our carbon emissions by about 3% as a result of all that policy, all those incentives. Yeah? The real drop in in carbon emissions in the UK took place before the Kyoto Protocol as a result of the end of the mining industry, moving us to a gas-fired electricity generation system, which improved the carbon efficiency of our grid electricity. And, of course, we shut down all of our industry and exported that overseas. If you take into account the embodied carbon emissions of all of our imports, yeah, our carbon emissions have risen in real terms by about 12% since 1990. So how does that compare with policy? Well, there's 2020, a further 24% reduction from where we are now. So we've got a decade to do it. We managed 3% in the last decade. We've got to do 8 times that much in the next decade. That's a really tall order. And we've got to continue on that trajectory right through the next 4 decades to 2050 to meet our commitments to protect the biosphere and, by the way, also to secure our energy supplies further into the future. This is going to affect everything we do. Everything. It's absolute nonsense to stand here, I'm afraid. I'm going to say it now. You probably get this impression from me in a minute. It's absolute nonsense to stand here and say we can solve this by designing low-carbon buildings. No way. This is across everything that we do. It'll affect our lifestyles at every level, and we need to be thinking about it at every level. And, of course, the carbon figures, as I've mentioned just now, they actually hide some of the underlying truths because we've changed our fuel mix on the national grid. If we look at the same time period, 1990 to 2008, our total energy demand in the UK has risen continuously. The only sectors that have shown any reduction in energy consumption are industry, which is this, over time, a very significant, sort of nearly 50% reduction in energy demand, and agriculture. Now, why is that? It's because we've hived all of these processes off overseas. Everything we do at home shows a continuous rise in energy demand. And that's what we've got to address. We have become so utterly blasé about energy due to the abundance of fossil fuels that we just don't know how to manage it anymore. We won't solve it with this sort of thing. I'm sorry, utter nonsense. You can actually see it, can't you? Yes, good, you can see it from the back. Can you see it on the camera? Because this is... and I'm afraid... Can everybody read it? To put it in context, this is a 15 kilowatt wind turbine. If it was on a windy hillside in Wales or the North York Moors or somewhere like that, it would comfortably generate enough electricity for the total annual demand of 12 average houses. You stick it in a car park in an urban setting, and it can barely do enough to keep the lights on in the cafe. The problem is that when our local and national politicians adopt initiatives which people have voluntarily bought into to deliver better buildings or better services, when they adopt them into legislation, all sorts of things go horribly wrong. People started putting renewable energy on their buildings because they thought it was a good thing to do. It was a good thing to do. But whilst you still had the choice, you could do things that were sensible. As soon as we're forced to do things by legislation, we are forced into situations where you have to do things sometimes that you wouldn't otherwise choose to do. And I think this is a good example. Those turbines up there are exactly the same size and capacity as this one. Up there, the three of them together can only produce as much electricity as one of those. One of those costs about £60,000 to install. That lot, with all the anti-vibration and the protection systems and everything else, it's been a bit of a selling point, I must say, but the developers have been wowing us with the fact that this installation costs 1.3 million. So policy, legislation, adopting things that started out as voluntary codes and standards, things like FREng, things like the Code for Sustainable Homes, when people do them because they're worth doing, you can deliver tremendous advantage. But when you're forced to do them and it's inappropriate, you get all sorts of nonsense going on like this. For those of you who were here earlier, we had a bit of a discussion about domestic scale wind turbines. Well, the truth is that if you want to benefit from wind energy and you've got £1,500 burning a hole in your pocket, the last thing you want to do is to go down to B&Q and buy a domestic wind turbine. Because if you do, you would be lucky to generate about 4% of your annual electricity needs for your house. If, however, you got together with 1,000 people in your town and you each put the same £1,500 into a community wind system, like the cooperative at Westmill near Swindon, then your investment would return you 100% of your electricity requirements, with some to spare. I don't have anything against PVs in particular, but I've stuck them up here just to illustrate some of the things that, again, can go wrong when you adopt the wrong solutions. Unfortunately, PV works best when the sun shines. When the sun shines, it's generally warm and bright, and you don't need heating, and you don't need lighting. When you need heating and lighting, it's because the sun isn't shining. So PV actually relies on a form of carbon offsetting if you're going to use it widespread in the UK. If we put a PV panel on our houses, which is calculated to deliver sufficient carbon-free electricity to offset all of our usage over the course of a year, then actually that panel is going to generate most of its electricity in a 3 or 4 month period during the summer. During that period, you're generating far more electricity than you can possibly use. So you are relying on there being somebody else out there on the national grid who can take that energy and use it to benefit. But come the winter, or when the clouds come over the sun and your system is no longer generating, you are also relying on there being another generation source on the grid that can make up your shortfall. This is not renewable electricity for self-sufficiency. This is a form of carbon accountancy. It's a form of carbon offsetting. If every dwelling in the UK installed sufficient PV to offset their annual electrical consumption, then during a sunny day in July, we'd be generating about 85 gigawatts of electricity from all that PV. The total demand in the UK is only 45 gigawatts. You're generating twice as much as we can possibly use. So what do you do with it? Stick a couple of big cables in the North Sea and boil it dry so we can get to the oil more easily, maybe. But it doesn't add up. It's a form of carbon offsetting, and I have a bugbear about carbon offsetting because it leads people into total stupidity. Sitting in a traffic jam on the Euston Road in a petrol-driven van that feels good because his company has paid several £1,000s to a carbon offsetting company to go and plant trees in South America. Nature does not need our assistance to make trees grow. If you leave a patch of bare ground in South America, trees grow without our intervention. Paying somebody to go and plant tree seeds makes no difference whatsoever to the carbon balance of the planet. Actually, do you want to hear an embarrassing story about carbon offsetting? I'm convinced now that carbon offsetting was invented by accountants in order to have something else that they could sell us in a market that they weren't in. Do you remember the G8 summit at Glen Eagles? Do you all remember that that was carbon neutral, that summit? Because all of the air flights for all of the delegates coming into the UK were offset by the UK government. The offsetting scheme that they chose was to install low-energy light bulbs in a township on the outskirts of Cape Town in South Africa. Everything was set up and ready to go, but they chose to do the scheme through one of the United Nations schemes, which audits and proves that you achieve the carbon offsets. The idea was that the township would buy a whole load of low-energy light bulbs, they'd distribute them to their residents, they would generate a carbon credit by doing that, and they'd sell that carbon credit on the open market, and the UK government agreed to buy it as the offset for the G8 summit. The cost of employing the accountants, a well-known international firm based in London, to carry out the audit to prove the amount of offset in order to get the carbon credits was actually £17,000 more than the value of the credits that they could win from it. Yeah? The total carbon offset that they would have got was £37,000. The total cost of the accountants was £54,000. No carbon offset achieved. And then into the bargain, they discovered that the local electricity company in Cape Town was handing out low-energy light bulbs for free anyway, completely negating the entire scheme. So we're not going to get there by carbon offsetting either. Professor David Mackay has given us indication of what it might take to have a sustainable energy system for the UK. And this assumes that we make a significant amount of energy savings in our lifestyle, that we move into using hybrid and electric vehicles, that we achieve the best standards we can for retrofit and for new build, and we stop wasting energy at home by being sensible about what we do. And what this plan shows is that pretty much all of the agricultural land on the UK has to be turned over to producing biofuels, and the bits of land that aren't any good for growing arable crops are used for forestry to create wood chip. You've got wave and tidal barrages around the coast. You've got hundreds and hundreds of installations of incineration, waste incineration associated with every centre of population. You've got PV on every house in the country. These squares here represent 100 square kilometre wind farms. The ziggy-zaggy bits at the bottom represent 100 square kilometre photovoltaic farms all along the south coast. And if you do all of that, you would still need 8 solar collecting, concentrating solar power plants in the desert, each of them the size of Birmingham, in order to meet our energy hunger. It's staggering. It's absolutely staggering. And I wonder whether we're thinking about the right things when we're trying to address these issues. This is the McKinsey company marginal cost curve for carbon abatement. It looks at, on the horizontal axis, the total global carbon abatement potential in gigatons of carbon dioxide per year. And on the vertical axis, you've got the cost of implementing each of the measures. So a negative cost is a benefit to your economy, and a positive cost is out-of-pocket expense. Look at the possibilities, the opportunities for energy conservation. This is retrofitting existing buildings. This is switching all of your lighting to low-energy lighting. This is addressing our few remaining industrial processes as much as we can, because they've already pulled their socks up over the last 2 decades. Retrofitting residential heating and ventilation controls. Enormous potential there for carbon savings. all of them generating savings to the economy, because the less energy you use, the less new power stations we have to build, the less new infrastructure you have to add to the national grid to deliver the power. New building energy efficiency, by comparison, is minute, the potential, in abatement quantity terms. So retrofit is where it's at. Retrofitting existing buildings, not delivering zero carbon new buildings. We've got to concentrate on the retrofit message, which we've, again, had some discussion about earlier today. The government's focused on nuclear, offshore wind, small-scale renewables. Solar PV and high-penetration wind is the small-scale stuff you stick on your house or at the bottom of the garden if you're a farmer. And, of course, carbon capture and storage. And you see increasingly smaller returns for increasingly higher implementation costs. Overall, the total potential up here of the coloured bars is not that much greater. Sorry, I haven't coloured in all the bars down here, but it's not that much greater than all of the potential that you could win from energy efficiency in the first place. And just to show you where it's coming from, these are the four main sectors: industry, which includes agriculture, transport, the domestic sector, and commercial, which in this case includes commercial, public and private services. There's a little bit of renewable. Look at this. The renewable proportion of our overall primary energy consumption is absolutely woefully small at the moment. So to get from there to any kind of sustainable renewable energy plan, it takes enormous strides. And translate that into carbon emission terms, and actually you find that about 45% of carbon emissions comes from buildings. We know that the majority of the buildings that we're going to be inhabiting in 2050 are already with us, so that's the area we've got to address. We've got to address it by understanding where the energy goes in buildings. And when you look at the breakdown for typical commercial office spaces, 75% of the energy that's expended goes to making us comfortable, to making us feel comfortable, to keeping us warm enough in the winter, to keeping us cool enough in the summer, to giving us enough ventilation that we feel invigorated, and to give us enough light that we don't trip over our shoelaces. And if we could be a little bit more flexible about our demands of our buildings, you could make enormous inroads into all of that. So from my point of view, the priorities for a low-carbon society start with conservation. This is my little mantra. Conservation. Recuperation. Recuperation is a posh word for energy recovery. And then generation. Start with the conservation. When you've cut down as much of your energy demand as you can, use the energy that you've got remaining as wisely as possible. Use the same energy 3 times if you can. Take the heat from the back of your refrigerator and use it for something. Use the energy twice. Don't throw it away after one use. And then look at generation, using renewables where appropriate as part of a properly planned national infrastructure. I'm going to show you a few case studies. This is one of the buildings that Jane referred to in the introduction. This is the Innovate Green Office outside Leeds. Innovate was a developer of speculative serviced office space. And up until 2003, 2004, they did the same bog standard stuff as everybody else. In 2004, we got involved and we started to think about their buildings using building physics, using the principles of daylight, using the thermal properties of the building itself to control the environment, and then and only then installing energy-consuming building services as a supplement to the baseline comfort you can achieve. The building has no on-site renewables. It was built entirely out of concrete, wrapped in an enormous amount of insulation to give you the equivalent of an electric storage heater, a brick wrapped in insulation. You heat it up from the inside, it stays hot for an awful long time. It was designed and laid out to maximize daylight penetration so you can avoid the use of artificial lighting. There's an example. That's the central street between the office wings, which brings the daylight down into the building so the deep plan spaces can get daylight. It's got some fabulously complicated technical systems, which I'm not going to go into, but they're all designed to work in harmony with the building structure so that you're using the building structure as a continuous thermal store. This is how it performs. This was bang on. These are the national carbon benchmarks, carbon index benchmarks. And the developers' previous buildings hit the typical for air-conditioned offices in the UK, spot on. When we analysed them, they were about 1.5% different from the norm. This is what we achieved in terms of carbon emissions from the heating, ventilation, lighting, air conditioning, the regulated carbon emissions regulated under building regulations measured under BREEAM, etc. So that's an 80% reduction of the 75% that you need for comfort in the building. So it represents a 60% reduction in carbon emissions overall. It achieved the highest BREEAM rating at the time, and we believe it still holds the record as the highest BREEAM rating. In terms of retrofit, we've got an entirely different set of issues to deal with. This is a project which is typical of many of the jobs that we will have to retrofit in coming decades. A couple of adjoining townhouses to be converted as private offices. Retrofit makes the engineers, the designers' lives really difficult. For those of you who were here earlier and were listening to Peter, you'll understand. But just to show you an example, trying to put building services to the level of comfort that we demand from our spaces these days into historic buildings just becomes immensely complex really, really quickly. To solve these sort of problems, we need clients who are prepared to commit time to their projects. These are not easy issues to solve, particularly in retrofit. The construction industry is one of its own worst enemies in continuously promising to deliver construction projects in shorter and shorter timescales, which means you have no time to consider the appropriate solutions. All you can do is what you did last time. If you've got time, you can come up with some interesting options, interesting solutions. This is an installation of microbore capillary pipework plastered into the ceilings of the building, through which chilled water is circulated from a ground source system. So this is effectively replicating the thermal mass that you would get from a concrete construction by coupling these tiny pipes with effectively the thermal mass of the ground underneath the building. So you can take heat out of the building through its fabric and drop it into the ground where it doesn't bother you anymore. There's another example of the kind of things that we'll have to deal with, an infill site down in Southwark. Again, the design of these buildings addresses all of the issues to do with natural light, keeping the buildings open for air movement in natural ventilation. And this building uses a very similar system of cooling and heating to the one I just showed you. Only here, the pipework is much bigger, it's much chunkier, and it's simply embedded in the concrete slabs, which are left exposed. That's coupled up to a ground source system, and effectively the entire building frame becomes a hot or a cold radiator. You can absorb the daytime occupancy gains into the structure during the 8 hours of occupancy, and you can discharge it during the 16 hours that the building is unoccupied. So you cut down the instantaneous cooling demand quite dramatically. And there you go. There's a picture of heat pumps for anybody who doesn't know what a heat pump looks like. And that's the drilling rig on site putting down 26-metre boreholes to connect into the ground. But let's be clear. Let's be absolutely clear. Whatever we do with technology to make our buildings or our industry or our transport systems more efficient, at the end of the day, carbon saving comes down to people. Buildings don't consume carbon. Cars don't consume carbon. It's only when you get in your car and drive it somewhere that it consumes fuel. It's the same with our buildings. If we didn't make the demands, we wouldn't have this problem. And the demands are driven by our expectations of quality of life. Think about it. Think about the last decade or the last 2 decades. How much has changed in the way that we have handed over effort in doing whatever it is, whether it's at home or whether it's at work. We've substituted energy delivered at the flick of a switch for human effort. It's quite possible to bake cakes using renewable energy alone. But it takes effort. In order to use a sun oven, you have to continuously adjust its position every 15 minutes or half hour so that it follows the sun as it passes through zenith. And then you can bake cakes. You can even roast a chicken. Maybe not so often in the UK as you could in California, but on a bright sunny day, you can cook in one of these devices using nothing but renewable energy. But you have to make that choice, and you have to be involved in the process. You can't simply walk away from it and expect it to happen. And it's this attitude of walking away and expecting things to be automated for us that's giving rise to our disconnection between our personal effort, our wealth creation, and energy that it required to get it for us. We all say we admire the Mediterranean countries, don't we, because of their commitment to a food culture. But actually, when it comes down to it, how many of us are prepared to spend time shopping around different markets for different produce? No, we want our produce delivered conveniently. You know, it's all very well saying we believe in these things, but we don't do it. We don't act them. And even when you deliver the most energy-efficient supermarket in a decade, you'll still get criticised by some people for the amount of car parking. But the car parking isn't driven by the retailers. The car parking is driven by the planners. The planners are driven by people like you and I who vote with our feet. So whatever we do in these buildings, it still comes down to the people. And this was the reduction in carbon emissions from that store in Greenwich when it opened back in 2000. But it's our demand for convenience that is the driver behind all of these things. And yet, how more convenient can you get than the good old doorstep milk delivery? Think about it. You don't even have to go out, it comes to you. It uses the original eco-friendly electric delivery vehicle. And what's more, it comes in reusable glass bottles. Wash it out, use them again. None of this business with dumping it in a skip, smashing it up, grinding it up, reducing it to its component atoms, and then remanufacturing it and calling that recycling. You know, and yet we've abandoned all of these things. We've abandoned all of these ways of life. I'd love to know why. In the same time, our wealth creation has moved from being labour-based, and it's still labour-based. Let's be honest. 80% of the world's population still earns their basic wealth through the application of physical manual labour. We've moved almost entirely to an asset and information-based economy. Yeah, we just push electrons around which represent information, and we trade those bits of information to create phantom wealth. But in doing so, we don't create anything. We consume energy, but actually we don't create anything. And there's an even bigger issue, which I could talk about for another 2 hours, called entropy. Entropy is the ability of energy to do useful work for us. Free energy is converted to entropy when you use it to do work. Now, if you take that and you look at it at a macro scale, and it is applicable, believe me, but I can't explain why now, all the things that we do these days in our modern economy that we consider to be work are not work at all. The definition of work is to use energy to change a physical substance, either to move it or to change it into something else. We don't do any of that. We simply consume energy to do phantom work, which doesn't do anything to help reduce the entropy of the planet. That's another discussion for another day, but it's a big one. And of course, we're focused on cost savings. And we see that the planning of our cities and our urban centres are almost entirely driven now by saving cost. I have to confess, I've been involved in a number of low-energy sustainable schools projects for our local council, Bath and North East Somerset, which fantastically efficient, low-energy buildings. The kids love them. They work really well. But they give me pause, because actually what we've done here is we've allowed our local council to close down 4 or 5 local primary schools, 1 or 2 class primary schools, and consolidate all of that educational effort in one location. So all of those kids who used to walk to school now have to arrive by road. And it's this drive towards centralisation and drive towards cost saving, which is pushing us in another direction, which is inefficient. And of course, the PFI hospitals. The only way you can make PFI hospitals to work is to centralise everything. Now, this is the recently completed hospital at Swindon, and so I had a look at our healthcare provision down in our region. If you look to the west of London, there's the M4 up at the top there. That's Bristol. That's Newbury. These circles are the only locations left with accident and emergency hospital provision. All the local hospitals have been closed down and their services centralised on 2 or 3 big PFI hospitals. That means that if you're unfortunate enough to live in Devizes, Devizes isn't such a small place. If you're unfortunate enough to live in Devizes and you fall on a carving knife or something equally dramatic in your kitchen, you are faced with a minimum 40-minute road journey to access a basic need. And this is what we're doing by not planning. I'm sorry, I'm going to be controversial about the planning system. We don't have a planning system in the UK. They don't plan anything. All they do is tell you what you can or can't do. It doesn't relate to any kind of future plan. Nobody is thinking about how we should be delivering our cities in order to make sure that everybody can access their basic needs in a low-energy fashion. And at the end of the day, are we costing the earth? Well, I said earlier that the construction industry is its own worst enemy, but actually it's bigger than that. The whole process of the property market in the UK is dysfunctional. The whole idea of building buildings that nobody wants in the hope that you can sell them quickly for a profit is totally dysfunctional. The people who are putting the money into these buildings have no interest whatsoever in the ongoing energy efficiency, and to be honest, buildings procured like this are almost always terrible. We have to think, we not only have to rethink the way that we procure buildings and the way that we design buildings, we have to think about the way that we put different types of buildings and different types of activity together to create sustainable urban centres. There you go. There's a bit of a pipe dream. It's my pipe dream. But what we've got is we've got all of the aspects that you expect to find, but rather than piping in wind energy from a long way away, it's got to be nearby. We've got to make use of all the resources that we've got, and that means run of the river. If you think about the tens of thousands of mills built throughout southern England by the Anglo-Saxons, all of those sites have energy generation potential. We're just completely overlooking them because we're focused on the big bucks, big technology solutions. Tidal. Yes, okay, we get really upset about the idea of destroying habitats. But if we want to carry on living the way we are now, we're going to have to deal with these issues. All of our power stations need to become co-fired so that we eke out the remaining access to fossil fuels by mixing it with incineration of waste, by mixing it with biomass. And biomass does not necessarily have to come from virgin forests. I think it's 50 megawatts, the power station out at Slough, on the Slough Estates. They converted to biomass about 6 years ago, and they get all of their biomass within a 50-mile radius of Slough, where you won't find a single forest. They get it mostly from waste from municipal parks departments. We've got to be thinking about using our effluent to our advantage. You know, we treat it, we pump it out to sea. Actually, we should be using it to create biogas, and then we should be using the sludge as fertilizer. We should be building our power stations next to our industry and next to our housing, so you can use district heating. We should be building our sewage treatment plants next to our power stations, so you can use the biogas to generate the energy to run our cities. And you should put the farms, or in this case, the tomato greenhouses, next to the power stations and next to the sewage treatment, because you can use the sludge from the biodigestion as fertilizer, and you can use the carbon dioxide emissions from the power stations pumped into the greenhouses to promote growth. Think about it, photosynthesis. Photosynthesis is the reduction of carbon dioxide by plants. That's what happens. That's why we talk about biofuels being renewable, because plants grow and they sequester carbon. Wouldn't that be much more sensible than spending billions of pounds pumping carbon dioxide into an empty oil well under the North Sea? Use it to grow tomatoes, use it to grow exotic fruits. We're just not thinking in a connected way. This is what we've got to do. We've got to think in a much more connected way. But the first thing to do is to go home and look at ourselves. Because we're the people that can make the difference. And when we redesign ourselves and we redesign our behaviours, then we'll have a low-carbon society, whether or not you invest all this money in technology. Thank you.